Here's another problem solving using in a C circuit solving using complex numbers, right? So it says element connected in series across this sinusoidal alternating voltage, right? And these are some of the element of voltage across them is this. So basically, due to voltage drop, we can clearly see that E, right, is equal to V1 plus V2 plus V3 plus V4, right? Four elements connected across this and the voltage across them, right? And because these are vectors, it's appropriate that we represent them this way, right? So in the vectors that we can add them up directly like this, right? So one other thing we should pay attention to is that the things that we are working on here are of the same frequency, right? So you see, there's this, so the frequency are the same, right? Because we know that this here, this angular frequency here is a 2 pi f, and because they are the same, it makes it easier for us to even add them up, right? Yeah. So working with something like this means that each and every one of these voltages can be represented in complex numbers because you are trying to use complex numbers to solve them, right? So what this says is that if you are representing this V1 in complex form, it's basically the magnitude, the peak value, right? And then we have what's the name? This angle here, and we have 0, right? This just shows that the angle is 0, the phase difference is 0. This is 60, and we have this, and then we have 60, right? As it says, and this one as well is let's see, the peak is 30, and then we have what's the angle? We have minus 30, right? 30 degrees. So these are the ways of representing them in polar. And then here, what we are doing is that we are trying to see how we can use a calculator to solve these, right? Then how they are, and then the E itself to have its own representation, right? The E will be this way. We have 110, the angle, phase angle symbol, right? And then we have 13 degrees, right? So this is how the sun is represented. So this means that all this can be solved this way, right? Where we have this, let's see, right? So if you're able to put the calculator we are using in complex mode, we should be able to solve this easily. So clearly, this means that this V4 that we are looking for here. So determine the expression for the V4 for the fourth voltage in this form, right? So we want it in the what do you call it, the phase angle form, right? Yeah. So this V4 here is here the E vector minus the V1 vector minus V2 vector minus V3 vector, right? Yeah. So let's see, and we know the representation for each and every one of these, right? So let's see. Just have to go to the respect to the calculator that you are using. You can go to the complex mode, and then when you have the answer, you choose the unit that you want it in, right? So we know this what we are going to need to find the V4, right? Okay, so we are in complex mode already, so complex mode, complex, right? Right, and we are trying to find the V4, right? The only thing that we need is for us to be able to find this here, right? This symbol in complex mode, right? Okay, so let's see. Now we are trying to find that out. Okay, so the V4 is what we're trying to find, right? So E is 110, right? And then the symbol, and then the phase angle is 30, right? So I need 1, 2, 3 minus 1, 2, 3, right? Okay, the first one V1, we have 30, the phase angle being 0, right? The next one, we have it being 60 with this, right? The phase angle being 60. 60, V3 30, phase angle being minus 30. Remember, we are not when we have it in this format, right, we are not using the trig, right? So basically that will mean that you should not do the computations in rad. It must be in degree, right? So this here, I'll have to change it to degree, right? So let's see. I have to change this to degree. So degree now, right? So this is what we have it. But then the question requires that it's in this form. In this form, right? So as such, looking at this very well, you see it is not in the form that we need, right? It's not in the form that we need. So that's what we do. Just have to shift it to complex. We are in complex mode already, right? So but helps you, that's the way you can have the calculator can help you to do the conversion, right? So you see on this two here above it is complex, right? So I press the shift, press the 2, takes me to complex, right? And then the format that we need is this form, right? Which is let's see, the one that we have the magnitude, we have the W, and then the WT and the phase angle, right? We can find that the WT is constant there, right? So don't even need the phase angle, which, so the one that will see the format is this one right here, the R, then the angle, right? So let's see. If I press that, let's see. If I press answer, oh, we should go up. Okay. No, the computation we just did. Okay, so that's 110 this angle, and we have 30, right? Okay, and you have minus 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 30 angle 0, and then we have 60 angle 60, and we have 30 angle minus 30, and that's what it gives us, right? So if we want to do the conversion, shift complex, we need it in this format, this, right? Yeah, so it gives us this directly, right? So that will mean that the v4 that we are looking for, this v4 that we are looking for is basically 20.28. Let's do 40p 5, and the angle is about 62.7710 degrees, right? So right, to write it in the format that we've been asked, so that'll be 20, right? Let's do 20.28. 20.28 sine, we know that because there was a name, the angular frequencies are the same, so that's, we can add them up directly, right? So they were W, there's W here, W here, W here, right? So we can add them up directly, right? So that will mean that it will be the same. The angular frequency here will be the same, right? So that will be WT, our angular frequency T, and then looking at this phase angle here, it's a plus, all right? So plus, let's bring this here, plus 62.7, which is approximately 63, right? 63 degrees. So this is the format that we have to do it in, and we basically have the answer for it. The next thing to do is for us to find RMS, because for sinusoidal quantities, the RMS is simple. So this is basically the V4, right? The V4. So the RMS of it, so that's the RMS of this V4 that we are finding, will be equal to the peak value, which is a 20.28 that we've seen, 2865 all over square root of 2. So that's quite simple. So let's see. So that's 20.2865 on root 2. And that gives us the RMS value for that one to be 14.3 dp, 3447 volts. Alright, so that's it.